Hello students, welcome to the second lecture in our mathematical methods, and especially we have started the topic of linear vector space. That was our first topic that we have to discuss, and in order to deal with the definition of the vector space, we have started with what is meant by an abstract algebra. The reason being that linear vector space and vector spaces, these are the topics under the abstract algebra. So that is why, first of all, a small introduction to the abstract algebra itself is required, and then we can proceed to the definition of the vector spaces, and then we can start doing some problems. Now, the point to be noted is that in order to solve the problems in the vector spaces, such as the checking linear dependence, what is meant by linear independence, what is the meaning of null space of a vector space, what is the meaning of orthonormal basis, and then function space, what is the meaning of normalizing a function, etc. So these are the practical problems that we are going to discuss for your first 2 units of the mathematical method syllabus. But for doing these problems, a knowledge of the group theory is not necessary and compulsory. It's not compulsory, but however, what is now required is, if you look at the definition for the vector space, the definition is in terms of abstract notation. Okay, so without seeing the definition, we can start doing some problems. Of course, that is possible. But however, in order to start the topic in a proper way, or in a mathematically accurate way, we would like to first of all define what a vector space is, and then what is meant by a linear vector space. Now, such a definition is based on abstract algebra, which means based on the abstract notation. So because of that reason, we have started in the last class what is the concept of abstraction, which means that we have seen some notations. Notations are very important. You are going to use some notation, and if that notation is written, then you understand that this is the meaning. So notation versus meaning, this kind of connectivity is very much required. So we are not going to write a lengthy English sentence for the explanation. That is a point to be noted. So abstract notation means only from the kind of or the style of writing down certain symbols, you understand what it is. So that is the fundamental point that you need to remember in the case of the abstract algebra. So let us see what we have done in the last class in 1 minute, so that actually we are essentially continuing the place where we left in the last class, and therefore I will show what we have seen in the last class, work. Let us see that. So this is what is done in the last class, and you can easily verify, or you can refresh your memory that these are the symbols that you have. Okay, let me bring the cursor. So cursor is not visible now. Okay, so here you have the different types of numbers that we have seen, and these are basically called the set. So technically we will be using the name set. This is only a few of them. Any set can be used, but these are some of the starting points, or these are frequently used sets. Therefore the symbols are very important, and most important is this set of real numbers and set of complex number. These two are very important, R and the C. And then the next important thing is the Z, which is the set of all integers. So at least these 3 are very important, and you need to know the way in which you write, and by writing that symbol, what's the meaning. That's very important. This is the first point. The second point is the abstract operator, which means that the abstract means the operator can represent anything. That is the meaning. Either you can use star. There is no hard and fast rule saying that this is the only symbol that you have to use. Okay. You can use a star. Sometimes writing star is difficult. In the books, of course, anything you can print nicely, that's fine. So while writing, possible things are, you can use a star, or you can use a small circle. You can even put a dot, not a problem. Even dot is accepted. The point to be noted is that none of these things like a star and a dot, they do not represent multiplication. That's the point to be noted. It can represent multiplication, but it doesn't mean multiplication. Okay, abstract means could be anything. Even for the addition and the subtraction also, you can use a dot. So that is why let us not use the dot here, because dot is too frequently used for the multiplication. Therefore, we prefer to use either a small circle like this or a star. Okay, but in addition to these two things, you can also use any of these symbols that are mentioned here. That means a plus with a circle, and then something like into mark with a circle, or you can have a square and inside the square you have a plus mark. So none of them represent addition or multiplication. So all these things are generic operator. That means it is a general operator. It can represent anything for a given problem. Once you have a particular problem, then the meaning of the operator will be given to you. So at that time the clarity will come, whether it is exactly representing the usual multiplication, or that it is representing matrix multiplication, or is it a cross product in the case of vector, what it is. So that clarity will come when you have a particular problem with you, like in a question paper, for example. That clarity will be given to you, and then you can proceed for the further calculation. So until that means when the statement of the problem itself is not available to you, then we will be keeping this kind of generic symbol, and that is what is known as abstract notation. So this is very important. The second thing is that in this particular place we have written the word operator, and now we are going to ask or we are going to make some specialization saying that an operator becomes a binary operator. Okay, not all operators are binary, so you need to know only when some condition is satisfied it is binary. The explanation we have seen in the last class, but the point that I would like to emphasize now, because we are recalling this, is this one which is written in the pink color. So you can see that all these things are written in pink color. The notations I have written in the pink color, and that is what is the important thing. Now the usual English sentence is written in yellow color, and which you are going to eliminate, or which means that without writing anything in the English sentence, only by writing what is there in the pink color, you should be able to understand. Now, this is what is known as learning the algebra in terms of abstract notation. Okay, that is what we say abstract algebra. So it could be a general thing. Okay? Algebra doesn't mean the traditional school algebra. It means that you're performing some operation. That's all about it. The word algebra means. So now give the attention or importance to the pink color one. What do you mean by a binary operator? How do you read? You read like this. X is an element in the set you have here. S means a set. What do you mean by a set is, the set can be a set of natural numbers like this, or the set can consist of all integers. The set can consist of all real number. Anything can be a set. So or it can be a set of matrices. Okay, so what is meant by a set, that also will be defined in a given problem. So that is called S. S can be a general notation. Once again, there is no uniformity. You can use anything. Several people use capital G for the set because it is like group theory, right? So people prefer to use capital G for the set. So that's a convention, but let us have S as a set, for example. Then what is the meaning of this is, X is an element. This symbol is an element, which means if you are going to have 1, 2, 3 for the Z, then 1 is an element, 2 is an element, etc. So whatever is an object inside that particular set, that is an element. So this is the notation. So X is one element in the set. Similarly, Y is also another element in the same set. Yes, that's the meaning of this. If this particular scenario is there, then X and Y, that means X is operated on Y. This is how you have to read. You should not read this as X times Y, X plus Y, nothing. Because star is an abstract notation. We do not know whether it is addition, subtraction, division, multiplication, or it's a matrix multiplication, or it's a differential operator. It's an operator, that's all about it, right? So you can't read like X times Y or XY, etc. Now what is this therefore is that it is X operated on Y. That is what is the meaning. So whenever X is operated on Y, then we will be getting a result. Result means some answer we will get after finishing the calculation. That result should also belong to, this is a belonging to symbol. That means that particular element should be inside the set. Belonging to means what? That inside that particular set, this result should also be inside. It is like saying that whatever you do, the final object should be inside my house. Okay, I am doing some work in my house. The resulting object should not go to the next house. This point is clear. That's the meaning. So then that is what is called the operation is closed under the operation. You perform some operation. We are going to get the result. That result should be inside our own set. It should not go outside. Now, if that happens, then we say that the operation is closed. And operation is closed is what we say closure. This is fundamentally important one. If the closure property is not there, there is nothing to discuss about groups. There are no group theory, there are no fields, there are no ring, nothing is there, no vector space. So therefore, binary operator is the primarily, or it's very fundamentally important topic. And the word binary, why it comes, I already told you that there are only two elements are there. Only two elements. Okay, so we know how to add two elements, we know how to multiply two, we know how to divide two elements. Given two at a time, we know what to do. Okay, so that's the point that you have to emphasize, and we are going to see what will happen in the next. Okay, what happens when it is three elements are there. So that discussion now we will continue with this. So these are the points that we have discussed in the last class. So if you are going to continue that, let us now discuss one more point, what is known as commutativity. I think commutativity is also discussed in the last class. So therefore, I will just write down in one line, only one line. Commutativity, what do you mean by that, and how do you write? You write it like this. When x is operated on, that's how you write. X is operated on, that star you try to write nicely, otherwise it will look ugly. When x is operated on y, and the result should be equal to y is operated on x. So if that kind of a condition is satisfied, then we say that the commutativity is satisfied. This is also we have seen in the last class. And now we are going to talk about what will happen when you are going to deal with more than two elements. We always say that only two elements are there, right? Suppose if I have three elements, what to do? So that situation is what we are going to discuss in right now. So let me therefore write down that. Okay, how to deal with three elements. An element could be anything like a matrix, it can be a function, but simplest situation is a number. So that's what I will write down. So the simplest case is a number is easy to understand. So as an example, if three elements are there, you consider adding something like 3, 2 and 7. So a simple question is given, 3 plus 2 plus 7, how much? That's the question. Carefully you have to see what is the answer. The literally answer is that we do not know how to add. This is the real answer. We do not know how to add three numbers at a time. Okay, so remember what we are doing. We know how to add, but addition is not three at a time. That's a point to be noted. And therefore, now we'll have to. We would like to know how to deal the situation. Okay, how to deal this kind of a scenario. That means three at a time. So that's what I would like to know. Three at a time we do not know. Therefore, but rather we know how to add only two numbers at a time. That's what we know, right? So that is exactly I'm writing. We will be able to perform addition with two numbers at a time. So, but now we have three of them. So therefore, how to deal a three number at a time is you have an option like this. 3 plus 2 you combine together so that you have two at a time. Or another option is 2 and 7 you combine together so that we have two at a time. So now you see, we always have two at a time when you combine them. So that's what we get. But however, what happens is you are having two options are there, whether this way to combine or that way to combine. So therefore, naturally you will get the question whether the results of these two types of combination will give the same answer or not. That question naturally comes. That's what I am writing. Will the result of these operations be identically the same? This question, why it comes, you understand, right? Because we have two options to write down, two ways of grouping them. Therefore, the question also comes naturally. So let me write down the answer. If the answer is yes, then we say that this is known as the associativity property. So you understand how a particular terminology is coming into picture. It comes naturally. It is not that some property is there in the book and then you memorize. Okay, we ourselves ask the question how to deal with three of them. Then naturally you yourself get different options of combination. Okay, and therefore whenever the result is same, then associativity is a property. So I am highlighting once again. This highlighting is the terminology that you will have to remember in the case of abstract algebra. So let us therefore write down in abstract notation. Okay, 3 plus 2 and all not abstract, right? That is a simple thing. In the abstract notation, how do you write this? A, then arbitrary operator, then B operated on C. Then if it is equal to, that if should be there. If it is equal to A and B you first operate, then that result you operate it on the C. and if the equality is satisfied, that is a point to be noted. Okay, if the equality is satisfied, then we will be saying the associativity. Now I would like to say once again that the star is representing a generic binary operator. Okay, generic means abstract binary operator. So binary is something that has to be satisfied, only then we can do this, as I already told you. And therefore let us make the conclusion then. If this kind of equality is there, then we say that the set will have the associativity property. Okay, the set capital S, whatever symbol that you are going to use, the set will have the associativity property. So this is the conclusion. This is the abstract notation that we have. So this is a very important point. Even though it looks very simple, this is fundamentally important. So let me therefore try to highlight. Okay, it's not coming. So which is having the associativity property is the set will have the associativity, not the operator. Okay, the set will have the associativity property. So how do you write this is that, let me finish this as yes here, because I used to say this particular yes here. Let me explain here. What I'm trying to say is when we have yes here, you need to have how the set will look like. The set will look like so many elements inside, but in that lot of elements, ABC should be 3 elements. Only then this ABC can be written down here. Otherwise we can't write down. So therefore, whenever you write something, these things has to be written down properly. That's the first thing. And the second thing is very important, that we are having 2 options for bracketing. You see that if you put a bracket like this, this is one way to write. Instead of this bracket, you can put a bracket for A and B. Then you have second option. So now the point to be noted is that this is called bracketing, right? Now, how many ways in which you can put the bracket, that you'll have to think. If you have 3 elements, that is A, B, C, only 3 elements are there, then how many ways in which you can put the bracket is, there are only 2 ways in which you can bracket. This is one way, B and C bracketing. This is another way, A and B. There is no other way. So if there are 3 elements, you have an option of 2 ways of bracketing. This bracketing is called associating. You are associating B and C together in one set and finish the work. And then once you get B and C as a single number, if you do B and C, I don't know, something will come, let us say X will come, then we say that A operated on X, where X is already simplified. So once again, you will be having only 2 elements at a time. Therefore, we will be always doing our calculation only 2 at a time, and therefore the star operator is always a binary operator. So even though 3 elements are there, we will not call it as a ternary operator. That's a point to be noted. Ternary operator means an operator is supposed to be acting on 3 elements simultaneously. That kind of scenario we never had. We never have it. We always have only one type of operator known as binary operator. That means for binary operation, only 2 elements are required. If at all anything more than 2 is there, you have to do some kind of grouping, or you need to do some kind of associating like this. Okay, that is called bracketing, and then reduce it into binary operator and then do the calculation. So this is a point to be noted. The extension means instead of ABC, suppose if you have ABCD, then what will you do? If you have ABCD, then you have more ways of bracketing, right? A and B you can bracket, B and C you can do bracketing, otherwise C and D you can bracket. So you are getting more number of options for associating or bracketing. And then how do you read this if condition is, you have to put the equality for all of them. If you have 4 ways of bracketing it, then all the 4 results should give you the same value. Only then we say that this particular set will have an associativity property. So that is a point to be noted. ABC is the starting point, like when you are moving to 3 of them, 4 of them, 5 of them, 6 of them. If the number of elements are increasing when you are performing the operation, then the number of bracketing like this also increases, and therefore that many number of equality, everything should be equal to all these things should be equal. If it is so, then we say that the set will have the associativity property. Okay, so this is very fundamentally important property, and that cannot be eliminated. If the associativity property is not there, once again, it's very fundamental and important that the whole thing will fail. Whole thing will fail means you don't have anything to group. Okay, the entire group theory fails. That's what I mean to say. So this is as fundamental as the binary operator itself. Okay, so this particular points are very important. Why it is that's why I'm emphasizing now. The moment you finish the binary operator, the abstract not the what you call the associativity property is fundamentally important, and you do not have any scenario where it fails. In case if it fails, then you cannot do any kind of grouping. Okay, so therefore this is very important and it has to be satisfied. That is what we mean to say. So let us therefore, I will continue this writing. So as usual, let me therefore write down where the set is given to you and the star will be defined in the statement of the problem. Okay, because star is arbitrary as long as which problem we are going to solve we do not know. But once the statement of the problem is given, what is star will be given. That's what I am trying to write. Okay, fine. So now I think A, B, C, D is over, right? So you remember D. D is commutativity over, and now we have associativity, right? So I want to give some number. So where is associativity? Okay, we can give E because D, A, B, C, D over. Now this is E. That means what? Like 5 properties you already know. Okay, that for that, in order to know how many properties you learned, I just want to give the A, B, C, D, E. So 5 of them you are quite familiar right now. And once this is clear, now we will see next important property that comes naturally. Okay, so let me write down that. So we are talking about now the subtraction and the division. We always say addition and then multiplication. Or then what happened to the subtraction and division? That's what I would like to say. You take a simple example like 2 minus 7. So how do you write 2 minus 7? It is equal to 2 plus minus 7. Therefore, our understanding is that subtraction means addition only. Finally, addition you can do. Minus 7 is a number, that's all. It belongs to some number, right? Let us say integer. Integer contains, set of all integer contains negative numbers. So it's just a negative number. So you don't have to worry about the subtraction at all. That's the meaning. So we are trying to eliminate some unwanted terminology. Subtraction and division is unwanted terminology. We would like to eliminate them, or we want to say remove it. Okay. If you say only addition, it's enough. That is the meaning. So I would like to make that point clear by writing this particular statement. So what is the statement that I am trying to say is that you have a negative number here. Now the point is that either you can use a negative number as a terminology, or that we are now using a different terminology, what is known as an additive inverse. Now why we are trying to bring this kind of a terminology is that there is an addition here. We are always talking about a binary operator. When you are talking about a binary operator, the same terminology should be there. If it is there, then we will be moving more comfortably. Sometimes plus, sometimes minus will come, and then sometimes inverse will come, sometimes division will come. Means, it appears as if too many things are there, and then it will be clumsy. To avoid this particular situation and then make the mathematics more elegant, this kind of terminology is used. So you only see that we are trying to change the terminology so that things look uniform and the word subtraction now disappears. This word is no longer required. Instead of that, we are going to say, you can say that this is negative number, but you see that once again negative, we don't want to bring additional word negative. Instead of that, we would like to know how it is connected to addition. So that is how the terminology is coined here. This is called abstraction. Abstraction means some concepts should be made clear and then given appropriate technical term so that things flow in a very comfortable way. Since we are talking about the addition as an operator, additive inverse means additive inverse, the meaning of the additive inverse of plus 7 will be minus 7. In what way you say additive inverse is that this particular summation should go to 0. So plus 7 is the value. Suppose minus 7 is the additive inverse. What is the meaning of that inverse is that if you add plus 7 and minus 7, it goes to 0. So any number, if you add it with its own inverse, it will always give you 0. So that is a kind of common kind of information you are bringing. It is not particular to number. You can do it for a matrix also. If you have a 2 by 2 matrix and if you take an additive inverse, remember additive, okay, not multiplicative, additive inverse, then what will happen? All the 4 elements in a 2 by 2 matrix will be the opposite term is minus of the original value. Therefore, if you add these two things, then you'll get 0, 0, 0, 0. Okay, that will be the 2 by 2 matrix you'll get in the case of matrices. So the concept is now extendable, not necessarily for a simple number like this. So we start with a number because it is quite easy to understand. Immediately you can extend the this kind of a discussion to the vectors, to the case of matrices, or to the case of polynomials. You can do for anything. Okay, additive inverse means putting negative of the original. That's all about it. So this terminology is the point to be noted. And if you are going to use this terminology, then the next question comes, what can be done for division? For division also we can do a similar situation. And therefore what happens is the word subtraction and the word division will be completely eliminated from the abstract algebra. Okay, so this is the point. Okay, then I will write down the corresponding example for the division. Now consider a simple example with the numbers 2 and 7 as usual. You have a 2 and you have 7, right? So let me write down 2 by 7. That can be written as 2 multiplied by 1 over 7. That is the idea. So that multiplication comes into picture. Now you see division disappears, and now we can say that I am only doing multiplication. And how do you understand this 1 by 7? 1 by 7 is therefore written as multiplicative inverse of 7. Okay, so you have a connectivity with the original number, right? That is a multiplicative inverse is a terminology that we are going to highlight. So therefore, let me therefore highlight once again, multiplicative inverse is a term that you will have to capture now. So inverse is the common name. Now let us understand that inverse is always there, common. So let us write down the conclusion. So what did we understand, or what did we learn in this discussion? So let me write down this kind of scenario demands or requires means demands that the inverse element should exist in the set. Inverse element should exist in the set, whatever set that we are going to consider. So I will write down the set under consideration. Whatever set we are going to consider to solve a problem, that set, that is the meaning of under consideration. So that is the meaning ultimately. So what you understand in our discussion is that there is something called inverse of an element. So this is common thing. So I am now combining both for addition and multiplication. The terminology inverse is very common for both of them. You can only add additive or multiplicative. Okay, so now you see how you are going to abstract. Abstract means more and more general. You don't talk about additive, you don't say multiplicative, you only say inverse. What is the meaning of inverse is, it is generic. Generic means operator inverse. So let me therefore write down clearly. Now what is the meaning of inverse is, inverse in this particular statement means operator inverse. What is operator? Addition is operator, additive inverse. Multiplication is operator, multiplicative inverse. That's what I am writing. Therefore I will write down that this means additive, multiplicative, not necessarily these two, it could be anything. For example, matrix, it could be matrix inverse also. All kinds of inverses will come into picture. For example, differentiation and integration is also inverse of one another, right? If you know the integration is the opposite of differentiation, that is what is some kind of inverse here. So the terminology inverse is generic. That means operator inverse is a generic terminology, which means abstract terminology. So this is the lesson that we learn in this small exercise. Now, because of this particular discussion, what happens is there is some special situation coming into picture. So I'll write down that because of this inverse, okay, because of this inverse, what happens is a particular case or a special case comes into picture. Now let us consider an example. We have 2 minus 7, right? Now instead of that, what we will do is, instead of 2 minus 7, you consider 7 minus 7. Now how do you understand 7 minus 7 is that original number together with its own inverse. That is meaning. Okay, let me first write down simple thing. We add 7 with the inverse of 7. You take the original number is 7. What is the additive inverse of 7? That is called the inverse of 7. Then we are going to add these two. Okay, then what will you get? I already explained, of course. So let us make things clear by explicitly writing. So if you do this operation, we always get 0. So always get 0 is important. Okay, not for only this problem. For every problem, what happens is whenever you take original number and then take its additive inverse and then add it, we always get 0, and that 0 must be belonging to our original set under consideration. The set under consideration means whichever problem that we are solving, that set. That's the meaning. So that will be available in a question paper. Okay. So once this is clear, coming to the multiplication part also very similar. So I will repeat it for multiplication. 7 times 1 by 7 you have to do. Now we will get 1. So now we will not get 0. So in the case of multiplication, when you take a product with the inverse, you will get 1, not 0. So our conclusion is that the special case is 0 and 1. The special case is 0 and 1. So that is the point to be noted. And in all the cases, our this kind of number, that is 0 as well as 1, must be present in the set under consideration. That is very important. That's what I have written as a last line. So if you want, I will highlight that. That is very important point. Probably I will highlight that. That 0, whatever result that you are getting, that must belong to the set under consideration. Similarly, if you are going to consider multiplication, 1 must exist in the set under consideration. If it is not existing, that's all gone. There is no group. Grouping is not there. Group theory is not there. You don't have vector space. Gone. So that's what it is. It's very fundamental. These are the things that it should exist. If that number itself is not existing, then you cannot perform further calculation. So let us therefore write down this conclusion. I'll write down this conclusion once the things are clear. The numbers 0 and 1 are special case. How do you know special case? That's what you see here. 1 minute back I have written. Yeah, that is, you're able to see. I will highlight that. That is a special case. So right now we are discussing the special case of additive inverse and the multiplicative inverse. So it is called self inverse. Original number with its own inverse. Okay. So once this particular concept is clear, our conclusion is like this. The numbers 0 and 1 are special cases, and they are given the name because they are special cases and they should also exist always. We give some special name for that, and that name is the identity element. The identity element of the set. So remember once again, identity element is generic, which means abstract. It doesn't tell what is the operator. If addition is the operator, then 0 is the element. If multiplication is the operator, then 1 is an identity element. So therefore, identity element doesn't tell what it is. It doesn't tell. You have to decide depending on the operator. So therefore, that point I will write down separately, this particular point. Note. What is the symbol therefore given to the identity element? Okay, the identity element is generally denoted by the symbol E. Because we do not know 1 or we do not know whether it is 0. What it is, we do not know. Okay. Only if the operator is known to you, then only identity element can be understood. Until that, we keep the symbol E. Therefore, small letter E is used for denoting the identity element. And if such an identity element is not present, if it is not present in the original set, then there is no discussion about the group theory. There is no discussion about vector space. That's what I am writing. So it is, these things are crucially important. They should be available in order to perform further calculation. That's all. Okay. Identity element should be present in the system. Inverse, operator inverse must exist. See the must, that's important. That's why I have written must here. It's not optional. It must be there. If it is not there, that's all. There you can't do any calculation and then close your book. That's the meaning. Okay, so now A, B, C, D, how many we have done? Do you remember? Something like A, B, C, D we have written. Let us go back and verify otherwise. Yeah, we have finished up to E, right? Associativity. But what about A, B, first one? So the other thing, hopefully you remember the first one, yeah. What are the different types of number, etc. And D is, yeah, C is binary operator. The meaning is closure. D is commutativity. And then we have the E. E is associativity. You understood now. So once associativity is E is over, now where is F? So F, what we can give? F is in inverse, right? So inverse is next important topic. Therefore, the property F is important. So let us say that this is F. And once we finish this inverse, next important topic is the identity element. Okay. So let us give the identity element as G. Okay, so just I am going back and coming so that I am giving the correct label A, B, C, D, E. So G. So that means point number A to point number G. These are fundamentally important things whenever you want to perform mathematical operations on a given set. Okay, that's fine. And once these are the basic things, quite simple. There is no complication. So once these things are clear, maybe we can take an example. That's what I'm trying to, let me take an example now. It's a simple example in order to demonstrate or in order to make the things clear. Whatever we explained should be clear, right? So let us therefore consider, what do you want to consider is, consider a set of all integers. That means capital Z, double stroke to capital Z, double line is there. That is the standard symbol. Consider the set of all integers, and that is what is given to you. And in addition, you also consider the binary operation to be division. You consider the binary operation to be the usual. Usual means the standard school calculation, elementary calculation. That's the meaning of usual. Okay, because there are other types of additions are there like modulo, division, etc. So to avoid the confusion, I am writing the word usual. Usual means the standard division. Now the question is that discuss the possibilities for the set to become a group. That's the question. Discuss the possibilities for the set to become a group. Okay, something is missing. The English is for discuss the possibilities for the set. For the set is missing. So let me write down that. Okay, for the set. Discuss the possibilities for the set to become a group. So the question is clear, right? Whether the set can become a group or it cannot become. That's the question. So trivial, it's quite easy to verify, but let us write down how do you proceed. First of all, let us write down what is this capital Z. It is a set of all numbers, so all negative numbers are there. Okay, you have infinitely many number. That's why I am writing with a dot there, and then it always goes up to infinity. That's all. That is the given set to you. And what is an operator given? Operator is a star. Star operator is a generic notation. Now the star operation is a division. So what is that we want to do now? We want to verify whether the given set can become a group. So that is the point. So that particular point, let me make it clear by underlining. Okay. So once division operator is clear, division is the job that you have to do. So let us consider any two element in the set. Consider any two element, because that is how you started from the last 2 days, right? So consider any two element. For example, 1 and 3. You can take anything. Okay, 0 alone you exclude for infinity possibility. Once you get a 1 and 3, you get a 1 by 3. But 1 by 3 it does not belong to, this is important, does not belong to the original set. Original set means given set. What is the given set? Capital Z. So that is what I always say, under consideration. Set under consideration means this is the set under consideration. In our problem right now, we are considering the set of all integers. This is the set under consideration. So 1 by 3, what happens is 1 by 3 does not exist. 1 by 3 does not exist in the set. This means that 1 by 3 is existing in some other set. That is the meaning. Does not exist in our set means it is existing in some other set. Whenever you have to move to another set for the discussion, we therefore make a conclusion that the possibility of making grouping is not possible. That's the conclusion. So our conclusion is that the division operator cannot be a binary operator. Cannot be a binary operator. So you understand what do you mean by cannot be a binary operator? Closure property is not satisfied. Why closure property is not satisfied? 1 by 3 is not there in our set. 1 by 3 is there in some other set. Okay, once it is not there in our given set, then closure property is failed. Once closure property is failed, there is no question of group, there is no question of vector space. Okay, let me make that statement correctly. And therefore, there are no possibilities for the given set to become a group. It's not whether it is group or whatever it is. It can be ring, it can be field, it can be anything. So I'll write etc. Okay, and that's all. That is an answer. So you understand how the problem is looking like and how you are writing the answer. So once the these concepts are clear, working out is reasonably simple, not difficult. Okay. So only thing is that we have to be carefully, you have to think carefully and then verify each and every element in the given problem. Okay, we will now take another simple example so that the concepts will become clear. Okay, the second example I would like to consider is that we'll consider polynomials. Okay, polynomials would be a very good candidate for discussion because always number means it will be boring. So we can consider polynomials. We can also consider matrices, but let me therefore consider a polynomial of degree n. A polynomial means you know how to write a0 plus a1x plus a2 into x square plus etc. plus an into x to the power of n. So and the meaning should be very clear, and therefore let me make it clear. What is that n means? It is the nth degree polynomial. Terminology is very important in abstract algebra. Okay, nth degree polynomial means you should be able to write your own. This expression will not be given in the question paper. a0 plus a1 etc. that will not be given in the question paper. They will only tell you nth degree polynomial. Okay, and this is another important thing, and let me finish writing, then I will explain. X is a real variable. Okay, real variable. Okay, so once this is clear, let me first of all explain where you have to give the importance and then how to proceed. So a polynomial and then nth degree polynomial is something which is important, and no more equations will be generally given in the question paper. They won't give you. So therefore it is you have to write the polynomial looking like this by your own. You have to write it correctly. Nth degree polynomial means maximum power will be n. That's all about it. That's the nth degree, and then the power of the x will be 0 here. So this is actually x to the power 0. a0 is there. Here a1 is there, right? X to the power 1 here. So this is x power 2. So this is x power 1, and this will be x power 0. So that's the meaning. So this is 0. So starting from 0, and it always end with the value n. If it is there, then it is known as nth degree polynomial. This is first thing. These things are important because terminology is going to decide your answer correctly. Otherwise, you'll make mistake. If it is given like this, it is not enough. You'll have to make the things clear in abstract algebra. You have to means the question paper. I mean, the question paper has to clearly tell what are these coefficients. Are they complex number? Are they real number? Whether these coefficients are only integers. What kind of number it is, that should be provided to you. If that is not provided, then we cannot write anything as its a solution, or we cannot write any answer for such a problem. So that is a point to be noted, and therefore the details will be available in the appropriate question. So in this question it is given that whatever a0, a1 etc., they are called coefficients. These coefficients, they all belong to this kind of R. This kind of R means what is this? This is the set of all real numbers. Set of all real number means it's very easy to remember. You write any number you like, okay, fractional, decimal, 0, plus, minus, whatever number you like, that is the set of real number. So this is the easiest thing that you can remember when compared to the other things. Okay, close your eye and write anything you like, any number you like, that is a real number. Okay, that's a point to be noted. So everything, whether integer, everything comes under the category, because every integer can be written as a fraction. 1 means 1.0. Okay, if you write pure 1, if you write, we say that it is integer. If you write 1.00, then it is a real number. Is this point is clear? So integer and a real number, what's the difference is, in the case of the real number, you always have a dot. Dot means decimal value. So 1 means 1.00, 2 means 2.00. Like this, you can always bring all the integer inside this R. So R is something which is easy to remember. That means any number you write, that is automatically a real number. So that is the meaning. And this also clearly tells you that these numbers do not accept complex values. Okay, complex numbers will not enter into picture. This is a point to be noted. If it is the case, then the polynomial is known as complex polynomial. So please note down here once again, I have written real polynomial. Real polynomial means that the coefficients a0, a1, a2 has to be real number. Very important. If it belongs to the complex number capital C, then this will become complex polynomial. So remember, the complex coefficients will be taken by Hilbert space. We are going to discuss about the Hilbert spaces, right? At that time, these coefficients, something like a0, a1, etc., some coefficient, whatever it is, don't worry about polynomial. This kind of coefficients will be allowed to take complex values. Okay, so when such a scenario happens, then we will be moving on to the Hilbert space. So that is why this kind of clarity should be important, and also you have to give importance to such points in abstract algebra. And the second point is that, okay, this is about the coefficient. What about x? X, what kind of x it is? X is also imaginary, real, what it is. It's a number or a variable. That's important. You see, give the importance here. This is variable. R means real number. Number is different, variable is different. So these are the points where you have to focus your attention, or you have to pay attention and spend some time to understand the question. Only then you will have to proceed to discuss the answer. Okay, if you just loosely see that, okay, it's a polynomial, then go further, means then you'll miss a lot. So that's why I'm taking some time, and then you'll have to give some importance. So you make sure that you give the importance to all these kind of terminologies whenever you read the abstract algebra. Okay, once this is the statement given to you, that means what? Statement is only given. Polynomial is there. Okay, polynomial is there. What is the question? So let me therefore write down the question. F of x equal to 0. Is this a polynomial? If I say only fx equal to 0, you have to tell whether the answer is yes or no. Because the answer is too simple, let me therefore write down that the answer is yes here. Okay, you have to tell clearly whether 0 is acceptable as a polynomial or not. The answer is yes, because you can now allow all the coefficients to take 0. a0 is 0, a1 is 0, a2 is 0, an is 0. If all the coefficients are 0, then what happens is fx becomes 0, and therefore 0 is accepted as a polynomial of nth degree. That's the point. Is it a polynomial of nth degree? That's the question. Answer is yes. It's a polynomial of nth degree. So this is point to be noted, because this kind of this kind of analysis in the given statement of the problem is important, so that you understand in a better way and proceed to the solution. Now let us take an example. Example 2 I will write down now. The set of all polynomials, I'll write down the set of all polynomials of degree 2 or less. Of degree 2 or less. So how this will look like? Okay, how this is looking like, that's what you have to write down now. It looks like this. S will be equal to, what is 1 by degree 2? You write down a0 plus a1x plus a2x square, and that's all. And that will be a degree of the polynomial is 2. Now you write less than that. Less than that means 1. This is 1. And even less than that, only C0. So now you must be able to understand what is written down there, and close the bracket. So this is important once again. Now what is written down here is a polynomial of degree 2. It's a second degree polynomial. So that is there here. And coming to this, and why do you want to write this, is that there is a point here, or less is there. Or less means less than 2, what is that? Less than 2 means less than 2 means what is the possibility? 1 is there and then 0 is there. So this is the 1, x to the power 1. Therefore this is the first degree polynomial, or polynomial of degree 1. And what is this? This is a polynomial of degree 0. So 0th degree polynomial, first degree polynomial, second degree polynomial. So this is what is known as the set of. Set means everything. All. The all is very important. All. What is the meaning of this all is, how many polynomials are there? If you ask the question, do you want to say 3 polynomials are there? This is 1 polynomial. This is second polynomial. This is third polynomial. Do you want to say that only 3 polynomials are there here? The answer is no. This is important. The answer is no. So what is the meaning of all? So this is important. What is the meaning of all is that you have to now ask the question, what is A0, what is A1, and what is A2? A0, A1, A2, they all belong to the real numbers. So if they all belong to the real number, which means that they can take any number in the set. Any number in the set means you can put some number here, A0, like 7.2, put a 3.2 here, put a minus 9.7 here. So that is one polynomial. Another polynomial, put a different set of numbers. For example, I'll put a 1 here, you put a 2 here, you put a 3 here. Okay, 1 plus 2x plus 3x square, another polynomial. Like this, you will be having a large number of polynomials. Practically speaking, infinitely many. So infinitely many polynomials of degree 2, infinitely many polynomials of degree 1, and then infinitely many polynomials of degree 0. That means set of all numbers, that's the meaning. So that many elements is what is known as all. That is the meaning of all here. So it is not 3. So therefore, now you see in the case of the abstract algebra, one has to be careful in thinking and then making a clear understanding of the question first of all. You take some time and understand what is the statement of the question. The or less is very important. If the or less is not there, then the story is completely different. So if you don't have or less, what will happen is you have to close the bracket here. Okay, you have to close the bracket, then there won't be any element of these two types. That is the meaning. So now you understand what is the statement written down. This is what is the given set for you. Okay, set is given. Next, what to do? We need an operator. Then some question will be there. So let me therefore finish this question, where the coefficients A0, A1, A2, etc., then B0, B1, etc., and then finally C0, they all of them are belonging to the real number means R. So everything is R. So that is given in the question. Okay. So whatever is given in the question, that has to be first of all captured. Only then you can proceed further. So everything is given. So now what is the question? Let me write down therefore the question now. The question is, what properties are satisfied under addition? What properties are satisfied under addition as the operator? Because operator should be given to you, otherwise you don't know what to do. So in this problem, addition is an operator given to you. So if the operator is given to you, if the set is also given to you, then the question is, what properties are satisfied? Which properties are satisfied? Because you already studied A, B, C, D, E, so many things. So you have to tell which of the properties are satisfied. So let us now see. It is very easy. We can quickly see now. Now the first thing that you'll have to see is that whether the given operator, what is given operator? Addition. Is the addition a binary operator? You can't always close their eye and say yes. You can't do that. You have to check it for every set. If the set is changing, then answer will change. So therefore, we will have to check the validity of the closure property. So whenever the question comes about the binary operator, it is directly nothing but the closure property. And you know how to check the closure property. Just now we have seen in the first example. This is second example. Okay, in first example, just now you have seen what is the closure property. Therefore, now you can easily tell what is the answer. Let us therefore write down properly. So let us properly write down a closure property implies what? If you add any two elements, that is the meaning. If you add any two element, but now element is a polynomial, right? So now you can write easily, instead of element, I'll write polynomial in the given set. In the given set, okay. So what we will get? So let us go back and remember what is the set here. So you have the first set of second degree polynomials. That is the one in some kind of yellow color. Green color I will show in the first degree polynomial, and then the last one I will show it in some pink color, the constant polynomial. I mean 0th degree. So the question is that what will you, if you are going to add any two of them? So add any two of them. That's what I am trying to say. So you should remember what to add. You have to add two types of polynomials. If you add, what will you get? We get, that's what it is, we get. Unless you understand, we can't write the statement. If you add, we get another polynomial of degree 2 or less. This is the answer. Unless you know, you have to add and see. Otherwise, you don't know how to write this answer. So that's why I'm going back now. You just take an example. So let me therefore give the importance to the or less also. How this kind of conclusion is coming is quite simple, elementary. We'll take a polynomial. Let us say that first degree polynomial I'll take 2 plus 3x. It's a first degree polynomial, green color. And then let us take a constant polynomial, which is put some number 9. Put some number and add. If you add, what will happen? I get 11 plus 3x. So what is this? 11 plus 3x. 11 plus 3x is the first degree polynomial. Is the first degree polynomial is inside the set or outside the set? Is it inside the set, right? That is the answer. So that's what I'm writing. It's a first degree polynomial. First degree polynomial means less than or equal to 2. That's what I'm saying, less than or equal to 2. And that polynomial is inside the set. This is very important, inside. Technically it is known as belonging to. Okay, in the abstract algebra we say belonging to. So let us therefore write down what is the result. The result of the binary operator, result means answer. The answer of the binary operator is belonging to the given set. That means present inside the given set, and therefore the closure property is satisfied. And therefore the closure property is satisfied. And that's all. This is what is the first property. So now it is very clear how to proceed for a given problem. Okay, this is one property. So let me therefore highlight when it's not coming. I'll highlight this. So one property is understood. Then what about some other property? We'll see now. So closure property is satisfied. So we are happy. We can proceed. If the closure itself is not satisfied, straight away throw. You can't discuss anything. Okay. So since closure is now satisfied, we are now ready to proceed further and ask what other properties are satisfied. So the board is now full. Somewhere I had to move. Okay, I'll move to another place. Okay, so since we have come to a new board, I will write down what is the set here, because that board has gone. So you should remember what is the set and etc. So simply let me write down what is the set here. Okay, that is the given set. Okay, closure property is satisfied. Put a tick mark. But what is the operator? So let me also write down the operator. The given operator is addition. The given operator. So that is important. Okay, so closure property point number 1 is satisfied. Okay, point number 2. We will check what about the inverse. Okay, we have already discussed what is additive inverse, multiplicative inverse. Now since the operator is additive, inverse means additive inverse only. So these are the points to be noted. So let us consider that. Consider C0. What is the additive inverse of C0? Minus C0. Is minus C0 belonging to the real number? That's what you have to write down. Is it belonging to the real number or not? Yes, it is belonging to the real number. That means it is belonging to our original set. So put a tick. Come to the first degree polynomial, b0 plus b1x. So similarly find out. So you write down b0 plus b1x. What is the additive inverse? So what is the additive inverse? Negative of that, minus b0 minus b1x. And this is also belonging to the given set. And therefore what happens is that both of them is belonging to the given set. Given set means capital S. So we are now successful in both the cases. Come to the second degree polynomial. So second degree polynomial is a0 plus a1x plus a2. A2, that is a2 I think, yeah, a2. And what is the inverse for that? Additive inverse. So that is negative of that. So write additive inverse is already, you know, additive inverse means negative of the original. So therefore, now you tell me whether the additive inverse is belonging to the original set or not. So once again, we are happy that the negative values that you got is also belonging to the same set. This is important. Okay, how do you know that it is additive inverse? Because given operation is addition. So our conclusion is that this particular polynomial, after making the minus, this is also belonging to the given set. So therefore what happens is, for all of them we are now successful. Put a tick everywhere, we put a tick. Therefore our conclusion is that we are now happy to say that the inverse is existing. Okay, that is a point, but let me also make one important point note here. I explained already. I will write it in green color. How many elements are there in the set? Not 3. So I already explained. Let me write down. The given set does not contain or does not mean only 3 polynomials. I already told you. The reason is that because it is set of all polynomials with the coefficients given by the real numbers. So that point I explained, but I did not write earlier. So I am writing now. But where from you, how do you know that it is a set of all polynomial means? That's why you have to be careful in reading the question. So I will go back to the old board and show you where is the word all there. It is there. So you have to now capture where is all, because it is not 3 of them. It is set of all polynomials. So all is very important. Okay. So it is not 3. Several of them are there. Actually, it is infinitely many. So therefore, you'll be now happy that any of these additive inverse that you get after putting a minus sign for that, all of them are belonging to the original set. So let us therefore make a conclusion now. The conclusion is that the inverse to each and every element exists. That is the conclusion. The inverse to each and every, that is important. That's what I am trying to explain. All means not 3 of them. Each and every element means polynomial. Each and every element exists. Not only that, not only existing, it is inside the given set. So both of them are important. If it is outside the set, once again gone. Okay, it has to be inside. So here element means polynomial. Therefore now the answer is clear. Now we are happy that the property of the inverse is satisfied. So now that inverse is also satisfied, what is the next property? Which property would you like to check? Isn't it? So we finished the closure. The first one is over, and then we finished the inverse. So once this is clear, now we can come to the special case. As I already told you, after studying the special case, after studying the inverse, I told you special case, right? That is what is the next one, namely identity. Let us check whether the identity element exists. Whether the identity element exists. Okay, if is missing, let us check if is missing. Okay, if identity, okay. So first of all, you have to understand what is identity element. Then only you can check, right? So first of all, let us understand what is meant by an identity element and how do you discover it. Answer is very simple. Let me write down. Answer is very simple. You have to do this simple calculation. You take a given element, one element you take. Then you take the given operator. So star, given operator star. Then you take its operator inverse. Okay, operator inverse to the original element. You take a original element, then take a star, then take the operator inverse of original. That's all. That is the answer. Okay, so here let us make it explicit. Take one polynomial, the operator is a plus, and then put the additive inverse of that polynomial. Okay, additive inverse of that polynomial. That is the meaning. You take any polynomial, write anything. Okay, let us take an example. Take some polynomial, okay, whatever comes to your mind that you can write, but make a note that star is the plus now in our problem. So therefore operator inverse is actually additive inverse. So these are the terms that you can easily refresh your memory. And then let us take an example. I will write something like 3 minus 2x. Then you write down plus. Then what is the negative of that? That is an operator inverse. Minus 3 plus 2x. So if you add them, how much will you get? 0. Whether 0 is belonging to the set? Yes. Yes, it is belonging. That is the point. Okay. So 0 is belonging. to the given set. So that is a point to be noted. So I'll make it explicitly clear by writing 0 belongs to the given set. Okay, so how do you know that is C0? See, because of C0, all numbers are there. 0 is also there. So because of the given problem, if you see the coefficients, etc., the things are clear. So our conclusion is therefore 0 is existing. Therefore our conclusion is that, and therefore inverse for each and every element in the set exists. And not only that, the inverse element is also present inside the set. Okay, and not only that, the inverse element is present inside the set. Present inside the set is called belongs to the set. That is the meaning. So I will highlight these technical terms or whatever terms where you have to pay attention. Okay. So inverse element is present inside the given set. So this is important. So now this property is also satisfied. So let me put a line here. So let us go to another property, because this is also successful, right? See, whenever failure happens, we have to stop there. Now that everything is successful, the next we can go to the next property, namely we can check now the associativity property. Okay. We can check whether the associativity property is satisfied or not. So now what we have to do, as usual, you know what is the meaning of that. For associativity, how many are required minimum? Minimum we need 3 polynomials. So take any 3 polynomials. So these are the things you have to understand. Associativity means minimum 3. So take any 3 element from the given set, any 3, whatever you like. And let me therefore write down some arbitrarily some P0 plus P1x plus P2x square. If you want, you can write with some numbers also. And then second one, I will write down Q0 plus Q1x plus Q2x square. Second polynomial. Third polynomial, I will write it as some constant polynomial K0. And that's all. Any 3, right? So I am simply writing 3 of them. Now, the first polynomial I am putting a bracket. That is the second polynomial I will put bracket. The third polynomial bracket. Now the addition or the operator is addition, right? That we have to perform. Now you already know that this is the one polynomial, the next or any other second polynomial, whatever it is. That's all fine. But the question is, for the associativity, you have 2 options of bracketing. That is important. You have 2 ways of bracketing. Therefore, we have to once again write this. Okay, we have to write the identical thing. A copy of that I have to write down. So I will move to another place. I will simply write down a copy of the same thing. That means I am going to copy this, because we have 2 ways of grouping them, or we have 2 ways of bracketing them. P0 plus P1x plus P2x square. The next one is Q0 plus. That's all. So now let us now go for bracketing. How to put the bracket? You put a bracket there, these 2, and then finish the job and then do the last one. This is one option. This is called associativity, right? This is one way that you can do. So you should remember, I already explained you associativity means 3 elements you don't know how to add. That is why we have to do 2 at a time. We are now doing 2 at a time. Now let us add the last 2 in this option and then finish the job and do the first one. So you have 2 ways of associating or bracketing. So this will be the right hand side result if you simplify, and that will be the left hand side result if you simplify. So you have this is the LHS result. Result means you have to simplify and get it. And after finishing the simplification, you'll have to compare and check whether they are identically same or not. So let us add it. It's very simple. So let us add quickly. There is no explanation. So simply we can add it and then write down. You agree, right? That is the total. Now what will happen to the right hand side? You will get the same answer. You can easily verify that you get the same answer. Now why you get the same answer? There is an interesting thing. The reason is because of the commutative property. So this point has to be clear to you. That's why I am explicitly writing. Now how this expression has become equal to the right hand side is because all the coefficients are real numbers. Okay, they are all real number, and real numbers will obey commutative property. Real number means 2 plus 3. 2 plus 3 is 3 plus 2. Because of that reason this happens. So it doesn't happen just like that. Because the real numbers have the commutativity property that is reflected here, and therefore you are fortunate enough to write RHS equal to LHS, and therefore associativity is successful. So you at least able to now recognize and understand how we are proceeding. There is no difficulty. In understanding this. But however, what is the lesson that we are going to learn, that we learn from this example, is that we have come to a stage where we can formally write in an abstract notation. So let me therefore write down. Okay, you have a set S. You have a set S. And you have a binary operator given by star. These two things are there with you. It is there with you. Then what happens is, this is the interesting thing. Then what happens is, if you are going to have many properties satisfied, okay, for example, let me write down in that order. Let us say that the operator inverse is existing. Let us say that operator inverse existing. Just now we have seen an example, right, like that. And we will also consider a situation where the operator identity also exists. Okay. In addition to these two, let us also assume that associativity condition also satisfied. Okay, there is a scenario. Just now we have seen polynomial scenario. Like that, there may be many scenarios wherein these three properties are satisfied. So this is important. So I'll put a box now. Now we are writing in a very formal way that if only three conditions are satisfied, remember, only three conditions are satisfied, then let me make clear that the set will be a non-empty. Non-empty means empty box. Inside an empty box, what you cannot do any operation. That's the meaning. The closure I am writing because binary operator, the word means binary is closure property. Both are connected. So once you have three properties satisfied, now we have the group, and we write like this: S comma star is a group. So this is the formal way, mathematical way of writing down a group. You see how simple it is. It looks very elegant and very simple. Only three properties only it has to satisfy. And technically, how do you write? S comma star. This is the way that you will have to write down. And remember this. There is a point to be noted. How many properties to be satisfied? 3 I have written. Okay. This closure property need not be written down here. Okay. Generally, some textbooks, many textbooks, they also write down that the closure property should also be satisfied. But remember this point. The moment you say that the star is a binary operator, closure has to be satisfied. It goes implied. It goes without saying. Okay. Therefore, by closure property has to be satisfied for every problem, irrespective of whether it is a group, whether it is field, or whether it is a ring, whether it is vector space, whatever it is. Okay. As long as you discuss any mathematical structure, okay, under the abstract algebra, closure has to be satisfied. So therefore, that need not be written down as one property. It goes without saying. Now, what is then written down here is, over and above the closure properties, what are the properties to be satisfied? So under that list, only 3 of them comes as a minimal. This is the minimal. This is the smallest situation where you can group them and then make it as a group. Group them means you can collect and combine them. So you combine a set of numbers or set of elements and say that belongs to a group. So based on what condition you say that it is a group is that only 3 properties should be satisfied other than closure. Closure is by default it goes. So technically, how do you write? How do you write is that you put a bracket like this, then the given set will be S. That's why I have written the set will be given to you, the operator will be given to you. In the previous example, what did you consider here? The set was a polynomial set. The binary operator was a usual addition. These two things will be given to you. If it is given to you, then you can easily verify whether these properties are satisfied or not. If all of them are satisfied, then you say that the given set S under the star operator, okay, under the star operator is a group. It's an abstract group. Group means abstract group. That's the meaning. So group is the simplest thing that you can consider, because there is no much simpler mathematical structure than a group. Group itself is the simplest thing. The next difficult thing will be a ring. So let me therefore make that statement. First, let me make another important statement. You can now add one more property to this, because that also we discussed in the last class, and that property is known as the commutative property. So let me finish writing that. So in addition to this, so let me write down this particular statement. If in addition to this, so in addition is important. So over and above the previous three conditions, if in addition, the commutativity property is also satisfied. So we can say that it is a fourth property. ABC is there. I will write down that. It's better. D. I can write down D so that ABC is, then D will become. So if the fourth property is also satisfied, then what happens is, then interestingly, a small change you have to make. That once again you write down, open a bracket, capital S, comma, star operator, then close the bracket. Then E is a commutative group. So you are now introducing an additional term there known as commutative group. The previous one is just group. Just group means what? Non-commutative. So these are the two important terminologies. Let us make it clear. And here for clarity, I will write down non-commutative. Okay. So remember, group means always non-commutative only. Commutative means you have to explicitly tell that it is commutative. There is another name for commutative is abelian group. So I will also write an alternative name. Abelian is sometimes used, but the meaning of the abelian group is that it is commutative group. So you understand the group, two types are there. One is commutative group, the other one is non-commutative group. So non-commutative group requires only three properties. Commutative group requires additional one property. Therefore total number of properties is 4. Okay, so hopefully, so that should be a fairly sufficient information for this particular class. Okay, and so till now we have seen simplest possible examples. Okay, you now understand how things are evolving. It is not that I am straight away writing down the textbook definition, like writing down some 10 properties, and if these axioms are satisfied, then we will call it a group. Okay, it is not that you first of all write down all properties, memorize them, and then do the situation. It is not like that. So you have seen now that things are evolving in a very natural way. You started with the simple number systems, and then you are proceeding further, and you yourself know why the associativity has come into picture. Okay, because we do not know how to add more than 2 numbers at a time. Okay, if 10 numbers are given to you, we do not know. We can only add 2 at a time and then proceed further. So this is the concept of the associativity. And the commutativity is, of course, the ability to reverse the order of operation. So that is not always true, as you know from the matrix multiplication and vector multiplication. Okay, only for simple numbers it's true. So as you can see, why commutativity has come into picture and why associativity has come into picture, as you already know, and why the inverse and the identity element has come, which we have already seen. The reason for discussing the inverse, operator inverse, is precisely that subtraction and division, the concept is eliminated. We don't consider them as an additional operator at all. So operator is only plus and multiplication. The minus and the division doesn't enter into picture, but they are automatically taken care if you have the operator inverse. So the concept of the operator inverse is because of that reason. The minus and division is not considered in the abstract algebra. So that has been somehow renamed, and it has took that kind of structure or that kind of a name. And finally, you understand why identity should be there. Whenever you have an operator inverse, the original with inverse will always give you 0 for addition. The original with inverse will give you always 1 for simple multiplication. And therefore 0 and 1s are simplest examples of identity element. But this is not always true. In the case of rotation, I already told you in the last class, 360-degree rotation represents identity element. Okay, so 360-degree rotation means you'll have to write down an appropriate 2x2 matrix. Okay, so that 2x2 matrix is the identity element. So you can easily see that identity element is not just 0 or 1. It could be anything, and therefore the general symbol given is small letter e. So once this is clear, this is literally the foundation for the abstract algebra. And the important point that you'll have to remember is once again, see this board here. Probably you can see the board here. You have one set. This is very important. You have one set capital S and you have one operator. Remember, how many operators are there? Only one operator. Set also will be 1. So one set, one operator means we will be discussing group. Whether it is commutative or non-commutative, that's okay. It can be anything. But there should be only one operator and only one set. So the next question comes. Suppose if I have one set, suppose if I have two operators, what will happen? If I have two operators, will it be a group or not? So that is an interesting question. So that is a kind of extension that we are going to discuss in the next class. Okay, so let me stop here.